Hello everyone, my name is Abhishek and today I'm going to show you that how you can create a custom layout design using a freely able tool known as the Klayout. Just a general outline to this presentation which includes a general introduction to the Klayout, what are the different MOS layers, stick diagram representation, example of the stick diagram and the layout, and in the last we will be discussing about that how you can implement an inverter design using the Klayout tool. So just a general introduction to the layout. So layout or mass design is a representation of an IC in terms of planar geometries, which is mainly in the rectangular form, which is correspond to the pattern of metal, oxide, semiconductor layers that make up the components of an IC. As you can see from here, so we have the different layers connected with each other using the different vias or contacts, right? So this is a general top view of an IC. So using the layout, usually masks are created, which are used in the foundry for creating an IC. So this is the general MOS layer representation. So these are the different color codes which is provided to the different layers so that it can be more conveniently studied. Suppose for the polysilicon, red color is there for diffusion, green color is there for metal, blue color is there for contact. This kind of a symbol is used. For implantation, this kind of a color is used. Over glasses, this color, and buried, same color is used, right? So just a little bit about the stick diagram and why it is required for creating a layout. So stick diagram are a means of capturing the topography and the layer information using the simple diagram. Stick diagram also convey layer information through the color code, which we have shown in the previous slide. It also acts as an interface between the symbolic circuit and the actual layout. It also shows all the components vias in the design. It shows the relative placement of the components and where the wires should be connected. Goes one step closer to the layout, as before going to the directly to the layout, we need to design the stick diagram to see the different connections. It helps to plan the layout and the routing. For mainly this particular purpose, stick diagram is most important. So these are the stick diagram notations. For metal, this kind of a layer is used. For poly, this kind of a color is used. For diffusion, this kind of a color is used. For P-diffusion, this color is used. If you are using the buried contact, then this kind of a symbol is used. For contact cut, this kind of a symbol is used, right? So these are some rules. So rule number 1 shows when 2 and more sticks are of same type and crosses each other, which represent electrical contact. So as you can see, we have a blue color here and we have a horizontal line here, and vertical line is cutting this particular horizontal line, means that there is a connection between these two lines, right? Similar for this particular thing, suppose this is a poly and a vertical poly is cutting this line, means there is a connection, there is a poly connection, okay? Rule number 2, when 2 or more sticks of different type crosses each other and there is no electrical contact, then it can be represented using this. So without connection, it can be given like this, and if there is a connection, then it can be shown like this. When a poly crosses a diffusion, it represents a transistor. Okay, so suppose this is a poly and it is crossing our diffusion area, right? It represents a transistor. So this is a NMOS and this is a PMOS. But if a contact is there, it means it's not a transistor. Rule number 4. In CMOS, a demarcation line is drawn to avoid the touching of P diffusion area and N diffusion area. All the PMOS must lies on one side of the line and all NMOS will have to be on the other side. So suppose we have a P diffusion area like this one. So it should be separated from the N diffusion area by a particular line. And if we have more components, like we have more PMOS, suppose in the case of AND, okay, we have, suppose we have in the AND we have the two transistors, right, two input. So we have more PMOS here. So then we can, that PMOS should come near to this one on the top side. And in the bottom, another NMOS should be there, right? And in that particular way, connection should be made, right? So it's a general standard example which will show you how you can create an inverter and how you can create a stick diagram. So suppose, actually we missed this particular part. So here the color should be different. Okay. So this is for the NMOS, as you can see here. So NMOS is created here and poly is just crossing this particular line. Okay. And for the contact, drain contact, we have a drain contact here, and drain is connected by this particular part. So these are the drain connection, and PMOS source is connected to the VDD line, right? And NMOS source is connected to ground, and output is taken from here. So as you can see that we have the poly here. Okay, poly is connected, and we are taking output as, input as a V in this side, and output we are taking on drain side, right? So in the similar way, when you have created a stick diagram, then you can create a layout using that stick diagram. As you can see, we have also drawn a separation line which will separate the diffusion area of NMOS and PMOS, right? And here we are having the inverter layout, right? As you can see, there is a particular thickness of poly which depends upon the technology node, okay, that we have defined here, right? And we have the PMOS area, we have the NMOS area, right? And this shows the well, that is N well, right? And these are the metal contacts. This is the GUI of the Klayout tool. It shows the version of the Klayout is 0.26, which is the latest version. So now we need to create a layout. Before starting with the layout, I just want to show you the different functions of the Klayout. So this is just to select. This is to move the different layers. This is to measure the layout length and width. This is for merging two same layers. This is for the polygon. This is for creating the box. This is to mention the text of on the particular layer. This is to specify the path. This is for creating an instance, and this is for creating the partial edges of the shape. Now for creating the layout, new layout, just click on File and click on New Layout. So if you have integrated a particular technology, then it will show you here, but we are using the default one to create our custom layout. As we need to create the inverter, so I'm just mentioning inverter. You can choose the initial size of the workspace area based upon your requirement um, and based upon the technology node on which you are working. So we'll just change it to 1 micron. Okay, so the window which will get the workspace area which will get is of 1 by 1 micron. Click OK. So this is our workspace area, and in the bottom, as you can see, the length of the two box is 200 nanometer, that is 0.2 micrometer. Okay. To start with the layout, first we need to define the different layers which we're gonna use for creating the layout. Okay. So for that, just go to the edit and go to the layer section and click on new layer. So here you can define, suppose we are starting with the one and we need to create the NMOS. So we will be creating NMOS active area. To define the N diffusion, we will be defining poly. Just a second. We'll change the layer number to 2. We'll be defining poly. Then we will define PMOS active. We also need to define the NVEL for the PMOS. Because we are using the one well technology in which we have the substrate is of P-type. You can also use twin well technology, and there you need to define the P-well as well as N-well. Then we need to mention contact. The last one is metal. Okay, so these different layers we have. Now we can start with creating a custom layout. So first we're going to start with the NMOS. So first select a particular layer and just click on box. So we'll be assuming like we will be creating the NMOS and PMOS of 180 nanometer technology. Now up to this particular point, we have created the two active area or two diffusion area of NMOS and PMOS, as you can see from here. And as we are doing this for 180 nanometer technology, so we have created the poly as well. So let us measure the dimensions with the ruler. Just click here scroll it down. So this is approximately 0.6 microns, the length is, and the poly length is approximately 180 nanometer, as we are doing for this one. The width of the poly is 180 nanometer, and the width of the diffusion area is approximately 0.4. And for NMOS, the width of the active area is 0.2. The reason behind taking the double the width of PMOS is because of the mobility of the holes. As you know that the mobility of electrons is more than mobility of holes. So that's why we usually take double the width of NMOS in PMOS. And here also we are taking 180 nanometer approx. Okay. So I'll just remove the different ruler by Control Z statement. Okay. Now our next step is to create the contacts, right? Okay. Now we have created one contact, and now we have to create the similar contact for the drain part as well, and source and drain part of NMOS. So I'll just copy, so just click on it, copy, Control C and Control V, then click on move. Right? Now just check, cross verify the coordinates once that you have placed in the right place or not. So it's starting from 0.5 to this one, and then in the left we have. Now up to this particular point, we have created all the 4 contacts of PMOS and NMOS, and we have also created the NML for PMOS. Now our next step is to create the metal layer. So in the starting phase, we will create the VDD and VSS so that we can make the connections. Now we have created the 2 metal layers. One is a VDD and another one is a VSS. Now we need to create the contacts for PMOS and NMOS. So first we need to connect the drain so that we can take the output. And similar will do for the source and for the source of NMOS. As also we need to take the output, so I'm just drawing a connection to the output. So this is my V out, and similar I'll do for the poly. Now you need to check the coordinates as well, that whether these coordinates is correct or not, right? So by clicking on it, you are able to see the coordinates. After creating the design and creating the poly connection as an input, then you can define the different electrodes where PMOS source is connected to the VDD and NMOS source is connected to VSS. And we are taking output from the drain connection of the PMOS and NMOS, right? In this way, you can create the inverter layout. After creating this layout, you can save the layout in different format. Just go in the file section and click on save as. I'm just saving this on my desktop. So as you can see, there are the different formats available. Like you can create the GDS format. Then there is a TXT format is also there. Then .os format is there. .lef format is there for the synopsis tool. Then the Gerber format is there for PCB designing, and there are other formats too. So based upon the requirement, you can select the extension, and then you can save the design. And so when you save, then it will come up with this one, and here you can select your format. Then whatever the layer files, layers you have defined, then you can save the layers as well. This is a scaling factor, which is a kind of a multiplication factor to the initial grid, and then just click on OK to save the design. Thanks for watching this video. If you have any doubt, you can just mention it in the comment box. Thank you.